Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here every day in my virtual classroom. And come on, step on inside. We are going to be looking at similar polygons of some sort of nature here, where we deal with proportions and congruent corresponding angles and all things of that nature. I'm actually going to do back-to-back videos. These are practice problems that do relate a little bit with the lecture videos that I've given recently. So if you've seen some of those when it comes to, I forget what the section's called specifically, but there was one on corresponding parts. I think it was called something about corresponding figures or corresponding parts or something like that. So if you find that one, this video is going to be relating to that. And then the next one I'm going to do is about similarity of triangles. But here I have, I think it's 8 practice problems here that, relate to some of the things that my students did. It's kind of a solution guide for them for their homework as a result. So come on and check this one out with me, guys. Let's see what we have in store. So these first 4 problems, and sometimes I like to draw these, so maybe I'll give some space on the bottom. I'm not doing these ones on the bottom, so if it's okay with you, I'm just going to go ahead and clear these ones out down here. And we're going to look at this 5 through 8 to start with. And I'm going to start with number 5, where it says figure ABCD is similar to figure MNKL, write a proportion that contains BC and KL. Now, I'm not always going to draw all of these. In fact, this might be one of the only ones that I do draw. It depends on the problems. But to make sense of this, guys, here, is I have a similarity statement. ABCD is similar to MNKL. And I'm going to assume that you understand something about this prior to me doing this problem, meaning maybe you saw my lecture video, maybe you learned it from your teacher, whatever. But the basic nature of this is, with or without a drawing, I do have corresponding parts. A is the first letter, M is the first letter, B and N are the second letters, C and K are the third letters, D and L are the fourth letters. And that's not by accident as far as where we gotta place things if they were oriented the same direction. If I had some quadrilateral ABCD like this, and I wanted to draw this similar figure the same way, if it was just a bigger version, M would have to be here because it corresponds with A, it's congruent, and then N, and then K, and then L. And I think I want to do this one first in this way because I really want to talk about the segments here. A isn't just congruent with M and B isn't just congruent with N. The segments grow in a certain proportionality with each other. The segment AB and MN, they may not be congruent, but they do correspond in such a way that however many times larger this is than this is also, NK is also that same many times larger than this. Let's say MN is twice AB's length. Well, NK is also twice BC's length. That's how similarity works. Sides are proportional. So let's go ahead and take a look at the side lengths that they want us to be looking at here. They said they want us to look at BC, and BC corresponds with NK. So if we're going to write a proportion, we can do something such as BC divided by NK, and that becomes some sort of similarity ratio. Like I said, if BC was half of NK's size, then this would actually be 1/2. And then if we're going to have KL in the picture with this as well, we need to see what corresponds with KL in the smaller figure. That would be CD. So CD and KL correspond. Since I did BC over NK, BC the smaller, NK the larger, I have to do CD over KL in the same form. CD over KL, smaller to larger. And that is the proportion. That is the answer, or N answer. You could also flip it on its head. I could have put NK over BC equals KL over CD. That's fine. That goes large to small, as long as they correspond and they go in the same direction. Then you're good. Either of these proportions work as far as setting them up, this or that, and then of course swapping the equations. But that's it. That's good. And what I wanted to point to here is using the numbers, because this time I'm going to do the same thing here, only I'm not going to draw it. So this time here, based on the numbers, BC are the second and third letters, NK are the second and third letters, so they correspond 2, 3, 2, 3. KL was the third and fourth letters, CD were the third and fourth letters, so they correspond together. But of course, you also have to go from BC and CD are from the same shape, NK and KL are from the same shape. So you can't cross. I couldn't have BC and CD like that. Okay. Sorry for spending more time on number 5. I think it'll kind of help when I do some of the other ones. So let's look at number 6. Triangle DEF, 1, 2, 3, is similar to triangle STU, 1, 2, 3. Write a proportion that contains ST and SU. Okay, this one's a little bit interesting because this time ST and SU are part of the same shape, so we got to find the other parts that correspond to ST and SU in those respects. So ST doesn't equal SU, but when I divide ST by something in this other shape, it's going to be equal to dividing SU by something in that other shape. And it's really straightforward, guys. Are the first and second letters here. DE are the first and second letters here. So DE, that segment length, corresponds with ST in such a way that when I divide this by this, it'll be equal to dividing SU, first and third letters, by DF, the first and third letters there, as far as the segment goes for these two triangles. This is an example of a proportion. Once again, I could flip these together. That would be a proportion. But this works out with or without the drawing. The drawing helps, but also I want you to work on the letters in that same way. All right, triangle XYZ is similar to triangle XVW. Write the congruence statements that must be true. So congruence statements here are only with regard to the angles, right? Corresponding angles will be congruent. By the way, I want to give you a drawing of what this could potentially look like as well, because they do share the letter X, which is quite interesting. And actually, when it comes to a drawing, I might have to get a little more particular in what that looks like, because you know what my first statement's going to say? You know, this says XYZ, X is the first letter. That means this says angle X is congruent to angle X. Oh, you know what? There is more than one way I could do this. You know what? I can work with this. So anyway, here's a congruent statement. Angle X congruent to angle X. Let me show you more than one drawing for this that might help. Y is congruent to V as far as angles. Angle Y congruent to angle V. And then angle Z congruent to angle W. There's definitely more than one kind of drawing that I can do for this one now that I think about it. That is totally my bad. I was thinking of one particular version. Here's one version that you could draw, guys. I could have a triangle and then another triangle within there, and this could be the X. So this could be XYZ, like that, as long as this is maybe XVW. That way X is congruent to itself, Y is congruent to V, and Z is congruent to W. That's one example. Another example, very similar. You probably haven't seen something like this before. Maybe you have, I don't know. This could be X, and then this could be Y and Z. But check this out. Now this is V and W, like that. Right? So Y is congruent to V, W is congruent to Z, X congruent to itself, like there. The one that I was thinking of, honestly, off the top of my head, was if you have one of those kind of hourglass things. You know, something like this. So, like, X would be in the middle. And then if this was YZ, maybe you could have something like VW. There's more than one way to do these, of course. But the thing I was going to state about X is I can't just call this angle X anymore, right? Now I have to call one of them angle, you know, YXZ, and then maybe VXW or something like that, because there's not just a single X. So anyway, I'm spitballing beyond it, but what I'm saying is you're going to see some of those diagrams, guys. And what's often going to happen in those diagrams is you're going to have to come up with things being congruent to others because of reflexive property, because of congruent corresponding angles, because of vertical angles, because of alternate interior angles, things like that. So these drawings will surface. You are going to have to pull information out from them. Just be ready for them when you're doing them. Sorry again for lingering, but there you go. Actually, I can leave that. All right, number 8. Triangle MNP is similar to triangle HJK, and both triangles are isosceles. Okay. If the measure of angle P is greater than 90 degrees, name all angles that are congruent to angle H. All right, well, this one's a little fascinating because I was about to draw this. I was about to draw MNP. I was going to say, so say that this is MNP, but they just threw me a little, there's a little wrinkle in the problem. They threw me a little curveball. They said measure of angle P is greater than 90 degrees. Now, what's interesting about this, guys, is that P cannot then be one of the base angles of an isosceles triangle, because if you have base angles are congruent in an isosceles triangle, and you can't have an isosceles triangle with more than one 90-degree angle. So P being the only 90-degree angle means P is the vertex angle. Another way of drawing this for me would be P might be this guy right here. So maybe this is triangle M and P, like that. P is greater than 90. That means M and N must be. What they're telling you guys is M and N are the base angles. M and N are the base angles. And M and N are the first and second letters of this thing. So H and J are also the first and second letters of this guy. So if I have a similar isosceles triangle, let's make it smaller. How about? H corresponds with M, J corresponds with N, and K is the vertex angle here, which also, of course, is greater than 90. Now, they're saying name all angles that are congruent to angle H. We already know that H and J should be congruent because they are base angles of its own isosceles triangle. So angle H is definitely congruent to angle J. Well, guess what? Because these triangles are similar, any corresponding angles are also congruent. H is congruent with M because it corresponds with M. And M is congruent with N, and N is congruent with J. H is also congruent with N as well. These are all congruent to each other. H is congruent with J, congruent to angle J. is congruent to angle M is congruent to angle N. All four of these are congruent with one another, as an isosceles triangle would do, as two similar isosceles triangles would do in that instance. This information was just important to tell you that this is the vertex angle, and of course its corresponding part. Pretty fun. All right, let's move forward, guys. I got, I think, 4 more problems to do: 15, 16, 19, and 20, whether it matters to you what those numbers are. Let's look at 15 and 16 here. The figures in the picture are similar to each other. Find the value of x. Okay, I'm kind of, sometimes I'm not a fan of these problems as much because they don't give us the lettering. They're making us assume that we should trust how the drawing is giving us some information. Meaning, as these appear very trapezoidal, I don't know if they are trapezoids, but you know how this kind of looks like a trapezoid? A pair of opposite angles parallel, or opposite sides parallel? Right there, I have a longer base and a shorter base. Then that means, you know, this probably corresponds with this right there. And then this guy probably corresponds with this guy. I probably don't have a good way of putting that. But so they probably correspond in that way. One thing I would often recommend to my students is to maybe redraw them facing the same direction so you know exactly what does correspond where. Now, I have no reason to assume this is an isosceles trapezoid, meaning I shouldn't assume that this is just randomly x minus 3. But because they're similar, the best that we can do is trust the process of the stuff that they give us and work with it. Meaning, I'm going to take this image right here, this guy. I'm going to take this guy right here, and you might think, hey, let's flatten this thing out and put it like this, which is pretty good. The only real problem with this right now is x plus 1 and x minus 3 don't appear to correspond because one's on the right side and one's on the left side, and trust me, there is a difference. However, maybe this isn't really drawn the right way. We don't maybe just rotate it, maybe we also reflect it. Maybe this thing also is supposed to go this way. And I know the lettering gets weird, so let me fix those. So this was x plus 1 over here after a reflection and a rotation, and this is 6. Now we found corresponding parts here. And with that, because they're similar, corresponding parts are proportional, we can set up a proportion. So I can set up a proportion that takes the two corresponding parts here and divide them, maybe in this order, and that'll do the same thing here. Divide them in this order. So I can say x plus 1 over x minus 3, that equals 6 over 3. That's but one way to do it. There are, of course, multiple ways. You could choose to cross multiply, but you're going to see me play a lot with fraction reduction. In this case, 6 over 3, 6 divided by 3 is 2. So I'm going to turn that into x plus 1 over x minus 3 equals 2. Trust me, there will be many opportunities to cross multiply and stuff a little later, so we'll play with that when the time calls for it. All right, I need to multiply both sides here by x minus 3 because I need to bust their fraction, and I need to quantify x minus 3 over here. When I distribute, I will get x plus 1 equals 2x minus 6. The rest for me is algebra, so I'm not going to spend a lot of time on those parts. The geometry is the focus here, guys. Subtract x from both sides, add 6 to both sides, I will get x equals 7. So that is my value of x, guys. That is what keeps those things as similar as we want them to be. And of course, as I stated before, reorienting that really does sometimes help with finding the parts that do correspond. In that case, it also involved a reflection. All right, number 16. In the diagram, we have triangle NPQ similar to triangle NLM. So this time they tell you which ones are similar. That can help when it comes to a redrawing, finding corresponding parts, of course, when it comes to the numbers here, what parts go together. This is one of those things where, again, the ends are congruent. They correspond. You know, this is one of those hourglass things that I mentioned. We have those vertical angles, which are congruent, and of course, they do correspond. And they also tell us PL is 5. Looks like we don't need that for part A, because the x's are just the angles. Let's start with that, and then we'll dive into the PL later. So part A, find the value of x. X is referring to, or x is shown right here as the measure of angle L is 3x plus 18. Angle L is congruent to, L is the second letter here, P is the second letter here. So L is congruent to P right here. These correspond and they are congruent. Remember, there's no proportionality with angles. It's all about congruency. So I can set them equal to each other. And if you don't mind me going quick with this one, I'll go ahead and subtract 18, divide by 3, and I'll solve that guy right there. Okay, sorry if I'm arching my back a little bit because I had back pain for like the last month. Okay, so that's part A. Pretty straightforward there. Part B, find the lengths NP and NL. Now, in order to do that, it looks like I'm going to have to solve for y. If you don't mind, I'm going to go ahead and get rid of, not that, I want to get rid of the markings here, get them out of the way here. I got to solve for y, which means I got to probably do something with proportionality, with regard to proportionality. We got to find which parts correspond here. All right, so NP are the first and second letters. That means NL corresponds with NP. So here is NP, here is NL. They correspond. They're not congruent, they correspond. I can do some sort of NP over NL thing when I'm doing, assume this is, not assume, this probably is a smaller triangle, this is the bigger one. So NP to NL, that'll be equal to, and we have these labels here. Let's hope they correspond, because then we can solve for y that way. NQ is 3.2. NQ are the first and third letters. NM are the first and third letters here. That's NM, so that does work out. These correspond. And I can do the same kind of fraction. Again, it's all about similarity. NQ is in the first triangle there, like NP, and then NM is in this one. So let's see what we got, guys. NP is Y. NL, see, we don't have any information for NL, and I think this is where this 5, PL equals 5 is going to help us here, guys. PL is this entire thing right here. The entire thing is 5. How are we going to find out what just NL is alone? Well, if this is 5, and if this is Y plus what is 5? Well, we don't really want to say it that way. How about this? If this was 2, what would this be? Well, this would have been 3, because you got to do 5 minus 2 to get 3. If this was 1, 5 minus 1 is 4. But this is Y. You know what 5 minus Y is? Well, it's 5 minus Y. That's what NL is as a length. It's 5 minus Y. We use the whole length of 5. We had to use kind of this diagram to also work that out. Doing a triangle redraw wouldn't have helped us there. Only for corresponding parts, but getting this 5 minus Y is what we're going to do there. Anyway, NL is 5 minus Y. So Y over 5 minus Y equals NQ is 3.2 and M is 4. There's my setup. Now, I know a lot of people are going to want to rush to the calculator. I can tell you right off the bat, if you want to know, guys, that's 0.8. But I'm going to go calculator free in a way that I want to deal with fractions. 3.2 over 4, as far as, I guess this isn't reduction, but as far as simplification goes, if I multiply top and bottom by 10, I'm going to shift the decimal, so I get 32 over 40. That's kind of nice, because I can then divide by 8 on top and bottom, and I get 4/5. There, I like that fraction a lot more than 3.2 over 4. Now I can have fun with a little cross multiplication. How about that? 5 times y is 5y. 4 times 5 minus y is this guy right here. If I distribute, I get 20 minus 4y. I'm going to add 4y over. I get 9y equals 20. Divide by 9, I get y equals 29. And I'm going to leave y just like that. A decimal would only be an approximation. 2.2 repeating, I think. I think that's 2 and 2. I think it's 2.2 repeating. So I'm going to leave that as 29. So was that, I needed NP and NL. So NP is the same as y. So NP is y, which is 29. So that's the length of NP. And L is 5 minus y, which is 5 minus 29. 5, I got to multiply by 9 over 9, get a common denominator right there. That's going to give me 45/9. So NL is 45/9 minus 29, which is 25/9. And I'm going to leave that like that, which is 2 and so 2.7 repeating, about like that. All right, so anyway, those are the two lengths right there. Not always a fan when they give us a fraction as an answer. I really wish that, that didn't get bogged down in our nature of practicing everything else. I like the 5 minus y part. That's good. I like that they did that. But fraction answer kind of gets in the way of what you're trying to work on. Your focus isn't so much the algebra, it's more so the geometry, and that's okay. Not that fractions are algebra related. Okay, so there are those two. I have 2 more to do with you guys here. Number 19, is any pair of equilateral triangles similar to each other? Why or why not? And I don't think they're asking, is any one pair? I think they're kind of asking, is every pair? Or, well, I don't know. We'll see. But here's the thing about an equilateral triangle, guys, and this is something I kind of focused on in the last unit I covered. Equilateral triangles are also equiangular, and what that means is not just are all sides congruent, but all angles are congruent to each other, And in any triangle, all angles add up to 180 degrees. If they're all congruent angles, you can divide 180 by 3 and you'll get angle measures of 60. Now, I don't know if I had to state 60 for this, but the fact that all angles, they're not just congruent to each other. They are a constant number in every triangle. So it's not just, oh, these angles are congruent to each other and then these are. It's all of them are congruent to one another everywhere for every equilateral triangle. Mind the weirder number things. So a bigger version of it will also have 60-degree angles and congruent sides. So all this stuff here, congruent with respect to one another. So what that means is we found sets of corresponding angles congruent here, here, and here. And when you look at the next video, we'll know how that's enough information to say these objects are already similar. But also, the corresponding parts all being congruent to each other. If these are all unknown x's and these are all unknown y's, at least we all know that they're all the same, lengths with each other. So if I do an x over y on one set, that's going to equal x over y and x over y. All these sides correspond, whatever number that is, it's obviously the same, like 1/2, 1/2, 1/2. So all corresponding angles congruent, because they're all 60, with one another and with their corresponding parts. All corresponding sides proportional. Yeah, all equilateral triangles are similar to one another. Whether you grow and shrink it, it's just a bigger, smaller version of them. That's it. It's cool. All right. Figure CDEF is similar to figure K, L, M, N. Which statements are false? Select all that apply and explain why. My explanation will be based on the numbers, guys. I'm going to say them out loud, but as I give you a good old 1, 2, 3, 4, I'm not going to draw this. As I give you a 1, 2, 3, 4 and a 1, 2, 3, 4, we'll find out which parts don't correspond because of the number order. Now, I have not looked at these problems before. I haven't tried them. So the only thing I'm going to say is there might be a possibility where they do something like this. If they had, you see DE is letters 2, 3, and LM is letters 2, 3. If they wrote DE, you expect DE over LM at some point, right? But if they put DE over ML, I want you to know that that's allowed. That just because I did 2, 3 here and I did 3, 2 here, it's still the same segment. It's not in anyone's best interest to write that, but I don't know if they're going to trick you with that. This is still okay, that this was 2, 3 and this was 3, 2. Okay, I just want to make sure that that's known. Anyway, the other thing that we have to look out for, guys, is not just number order, but also whatever direction they go. So we got to make sure if we go from these letters to these letters on one fraction, we got to go from these letters to these letters on the other, meaning top, bottom, top, bottom. All right, let's take a look at them because I have not seen these yet before. So let's see. So my explanations will be verbal, guys. Maybe I'll draw a little arrow. I can draw numbers to show disagreements. Here we go. CD over KL, that's 1, 2 over 1, 2, okay? Equals EF over MN, 3, 4 over 3, 4. That one's good, so we don't select it because they're asking which ones are false. That one's not false, so I don't circle it. I'll just put a little true. That's true. All right. CF over KN, that's 1, 4 over 1, 4. Okay, those correspond. Equals EF over MN. EF is 3, 4 over MN is 3, 4. That one is true. Assuming these are similar. Did they tell you they're similar? All right, DE over LM. Hey, did I show you? Did I say we'd find those? 2, 3 over 2, 3 equals CF over KN. CF over KN. So far, these are all good. No problems. They're not having a lot of fun with this. I would have made a bunch of false ones because the thing I would have focused more on was explain why. All right, here we go. LM over DE. Okay, so now they went this one. So LM over DE. Still fine. They correspond. Just make sure they go this way again. Equals hang on, where am I? LM over DE equals KL over CD. KL 1, 2 over CD 1, 2. These are good. Good. All right. Last one, LM over DE once more. 2, 3 over 2, 3 equals KN over CD. KN is 1, 4. CD is 1, 2. Okay, that one's false. So we have a 1, 4 over a 1, 2. Those parts don't correspond. Those are not corresponding segments. That is not because of that part. This part's fine. That part's not. Man, they could have done a lot more with this when it came to tricking you, flipping things, and doing things like that. And I'm pretty surprised there. All right, guys, so that ought to do it for this one right here. I sure hope that was helpful as far as just looking at corresponding parts within figures that are larger. We're going to shrink down to triangles now only in the next video, which will talk about the angle, side, and side angle, side similarity conjectures all together there. Now, there's a lecture video that I have that talks about it. It's about a half hour long, and of course, I'm going to assume you have watched that before going into this other one to really make most sense of it. This next one involves some decimal problems. I've seen them already. I haven't done them all, but we'll take a look at that in a moment. All right. Well, thanks for watching this one, guys. Take care.